Hello, everyone. So today I'd like to go over the lab number 5, which talks about central limit theorem and normality. Let me go ahead and share my screen, and we'll see a little bit more about that. The recording that you have already there, I kind of took it down because I really wanted you guys to start working with the R scripts and maybe even introduce R Markdown. And I noticed that the previous labs were done utilizing the command prompt. We never really do that in R. So I figured let's go ahead and just do everything from scratch, right? So the first thing that you need to do when you're attempting a lab is go ahead and basically download everything, right? Create a little folder like this one and make sure that you put the codes and everything and the data in the same folder, right? Once you do that, go ahead and go to File, Save As, and I've already created one, so let's go ahead and do that. So you go to File and you create a new file and R script. So go ahead and then save that file as, give it a name, and make sure you put it at the same spot as where you are putting everything else. All right, so I'm going to go ahead and find, I guess this is under general and labs, and this is labs here and lab 5, right? So I'm going to find the spot where I kept everything, including the data. I'm just going to name it as, I don't know, like lab 5 code only. All right, so it is much better if you write your code in a script and execute it from there rather than the console, because then you can keep everything here and you can repeat it and whatnot. Okay, so after that, what I would advise you to do is go like side by side, have this over there and just follow along and try to understand what's going on. So the very first thing that you need to do is you need to read in the data, right? So now it makes sense to have the data at the same folder as the one that you have your code. That's why I insisted in the beginning of saving this code at the same spot as you can find the data. So if you try to run these lines, first of all, this line is going to load in the easy packages library, which I think we've already used in the past. Make sure that the libraries play very well together. And then I'm just going to be using ggplot2 and psych. These are the two basic libraries that we're going to need for this lab. Let's go ahead and load that in. But then if I try to run line number 3, it's not going to work because although I have the code and the data in the same folder, when you go here, it says, I can't find this one. But you can fix it by going up here to Session, Set Working Directory to Source File Location. That basically tells R that the directory that you're working, like the folder that you're working, is the same as the one that has the code that you're running. Okay, so that works only if the code is in the same spot as the data. So now if I run it, it's going to read it, and this is basically a list of samples that we had created here, and at the very end you have your means. All right, so in the notes we explained that basically these are 5,000 samples drawn at random from the uniform distribution that we discussed in class, right? So this is literally like choose any number between 0 and 10 following a continuous uniform distribution, right? And I did that, 10 different times, and I took 5,000 samples. All right, so there's a lot going on here. And at the very end, I have a column that gives you the means of each of these samples. All right, now let's go back and try to understand what's going on here. If you want to have like a first idea of how this looks like, there's a simple command I didn't include in the notes, but there's a simple command that you can put that is called head samples. And if you do that and you say, just give me the first 5, this will give you a glimpse of your sample. You will see that it has this many columns, and these are the first 5 rows. Okay, just to get a feeling of it if you don't want to check the whole thing. Now, what we want to do is we want to create a subset using number of observations. This is going to give us a good opportunity to figure out how to do subsetting by indices in R. And so, for example, if you want to keep the first 50 observation and save them as another subset, the command is like so. You need to just basically specify which lines you want. So with this command, I'm creating a new subset, which I'm going to call samples 50. And that is using the initial samples, and it's just keeping the first 50 rows, comma, all the columns. You signify that by just leaving that empty. So if I run this line, as you can see here, there's going to be a new data set being created, which is called samples 50. And if you look at it, it just has all the codes up and all the data up until line 50. All right. Similarly, you can do samples from any sort of range. So this is from 50 to 90. So again, I name it samples 50 to 90, and you just specify here with a semicolon which columns you want. This is going to take it sequentially. Now, if you want to create versions of this by selecting things from here and there, you can always do that by adding, like a C delimiter. So, for example, if you want to do, I don't know, you want to keep the first 50 and the last and then the 5090, so both of them together. So I'm just going to call this one test. This again goes out of the notes, but I feel free to play with these kinds of things in general. So this way I can just select basically the first 50 and then let's say just the 60th, right? Or I don't know, from 60 to 80 or something like that. So you can do it like this and then go 60 to 80 and then close it. And then all the columns, all right? So this basically says choose everything between 1 and 50 and then from 60 to 80. So let's test that and you'll see now, there you go, it has 71 observations, and as you can see, it goes all the way down to 50 and then jumps from 60 to 80. All right, and any sort of combinations can be done like that. So this is index-based subsampling. All right, now what do we need to do? If you want to focus also on only one column, you can call that again by just focusing on the column you want, and you can specify it here. So if I want to see just the sample means for the first 20 observations, first I'm going to tell it keep the first 20 observations and then only column 12. So if I click on that, you will see that this just yielded now not necessarily a data frame, but just the column of the means for the first 12. All right. For the first 20. So let's go ahead and explore that a little bit further. If you want, the other way that you can do it is you can just call it this way by focusing only on the column. And again, this will do the same trick. And now the samples mean 20 is again exactly the same. So there are many ways that you can call something, but this index-based subsampling is actually quite useful. The syntax there is row, comma, column. All right. So let's go ahead and try to explore a little bit the central limit theorem. And with the next code, what I'm going to try to do is I'm going to try to create the graph for that sample mean, but just the first 20 observations, right? And so if I do that, if I grab this piece and drop it into R, what this one is doing is basically choosing these 20 last numbers and is creating basically a very simple histogram. You can see here that the breaks of the bins are from 1 to 10 by 1, and you can just specify whatever you want, the name, the labels and all that. Now the Q plot is basically just something that has been used by ggplot, and you can change practically whatever you want. If I run it this way, I can see how it looks like. All right, so this is the histogram for the means for the 20 observations. And you could always save things, right? We're using the save command. This is going to save it, the histogram for the 20 means, and notice that it's going to save it at the same spot as the code, right? It saves it both as a JPEG and as a PDF, so you can plug it somewhere else. All right. Now, if I want to now do the same thing, but use the means for the 40 observations, one way to do it is obviously like create the sample mean for 40, and then do that, graph it. So the following part of the code is I'm going to copy in the first part of it. And let me put some indentation here. By the way, every time you put this, you're artificially making blocks in your code. So I suggest you do that, because this way I can just put these things, and what you could do is you could collapse this one if you don't want to see it anymore, which is kind of neat. And in general, you put comments in R by putting this little pound symbol. So for example, the first part is introducing the data set, and then we can just do some data description, and maybe then we'll have the graphs one after the other. So here, before we even do the histogram, we need to create the smaller sample, right, with 40 observations this time. And then when you do the graph for that, what you get is you get a similar graph, a similar distribution. This is the histogram of the means, and that looks a little bit more normal, right? Like we're trying to go to what we're going to learn today in class, that the more you do, the more normal it looks. Remember, these are the averages of observations here. So what we have here is for each sample, we're taking 10 observations, and the column of the means is the average of these 10, right? And we'll see that this, kind of starts to become a normal distribution, just like the one that it started off with. All right, continuing on. Again, this is saved as histogram 40, and let's take it one step further. Let's now create 400 samples by, again, selecting the first 400. And again, it is a good idea to put this little line here and then drop it. As you can see, I'm creating a new vector, which I'm going to call sample mean 400. And this is selecting the first 400, graphing everything. And when I do that, you see now that the histogram tries to become even more, symmetric and normally looking. Notice again that the mean is close to 5. And finally, whoops, there we go. And finally, let's do one which has 4,000 observations. And again, the same thing. Create a sample of the first 4,000 observations and then graph it. Little indentation here, and then just drop that there, copy paste it in, and remember, you select all the line, you hit run, and this creates the sample of the 4,000. And when you graph it, you get the histogram out. So there, this is like, getting closer and closer to a completely symmetric histogram. And of course, that is the case. Like, I mean, we discussed that as you increase the number of samples, as you increase the number of observations, it starts to look like normal. And this, remember, is a fixed number of observations in each sample, right? So it's a little bit tricky. So let's go back. And we continued on and said, okay, that looks normal. In a sense, if you were to draw a normal distribution on top of it, like an actual normal distribution with mean 5, then it would match up. But we had some means. We will now describe some means of basically make that visually obvious, and also talk about a test that you would use. I'm going to postpone the specifics of the test, but I would like to show you how it works for now. So what I would like to do first is create what is called the QQ plot. And the QQ plot is very simple. What it does is it finds the best theoretical distribution that approximates your data, normal distribution, and then takes your data. And what it does is it graphs next to each other as a X and Y plot. On the X-axis, it puts the theoretical quantiles for your data. And on the Y-axis, it puts the actual quantiles of your sample. So for example, which value in your sample is the median? That is which value in your sample is the mean? That is the 0th quantile, and so on and so forth. And it finds like all possible pairings and graphs them on this line. The closer the line is to the Y equals X axis, the more normal your data is. All right. So now I tried, for example, for the sample mean 4,000, you see that it's practically on the Y equals X axis, the line that goes from bottom left, top right, crossing this plane right in the middle. So that is the QQ plot. We will talk a little bit more about it in class as well and have like a complete description of it. But the code for that is very, very simple. If you're just doing it, you just use the command QQ norm. There are other ways to do it too. So for example, you can use the one that is designated in ggplot, and you can just use the stat QQ and stat QQ line like this. First of all, you need to kind of turn this vector into a data frame, and that's very simple, right? We just, name it df, and you can just say this y is the y equals sample means 4,000 is a data frame. When you run it, the only thing you do this way is just basically change it into a column. And then when you graph things in ggplot, you need to say what data frame to use and what's going to be on the y and x axis. In this situation, we're going to have the sample on the y axis, and this 4 should not be there. It should be just like that. Okay, so let me run this. So when I run it, what I see is there. Something didn't work out, or it did. I'm not sure. Okay, let's call this one P1. P1, let's run this guy real quick. Okay, and then let's run it and we'll see what I'm talking about. And again, this is the bare minimum. But again, with ggplot, you can add whatever you want. You can add x-axis, y-axis names, and whatnot. Okay, so this is a quick and dirty version with the QQ norm, but then with this version, you can just go all out with the graphing. Okay, so that's the code for the QQ-plot, but then the QQ-plot is just a visual expression, right? We would like to have a mathematical way of doing things, and the best way to do it is some sort of normality test. We will spend a lot of time on normality tests later on when we learn a little bit more about what they are, and these are inference tests. So for now, the way that I'd like you to use it is apply what is called the Shapiro-Wilk normality test. That's one of the normality tests that you can use, and this is just a very simple command, Shapiro.test, and then you just put the set of numbers that you're trying to find. And this basically gives you a numerical value, the p-value here. This is set up as an inference test, and basically it says the null hypothesis is, well, this data set does come from a normal distribution. The alternative is this test does not come from a normal distribution, and getting a p-value that is much larger than 0.05 or something that's like 0.45 or whatever here indicates that, yeah, this sample could be coming from a normal distribution, right? You reject the null hypothesis and claim that no, this sample does not come from a normal distribution if the p-value here is smaller than 0.05. So for us, that we don't know exactly what inference test is for right now, I just focus on this. If the value that you get here is smaller than 0.05, then maybe your data is not normally distributed. If it's greater than 0.05 and actually just make sure that it's bounded away from 0.05, then it is normally distributed, right? So a value of 0.45 is pretty good. That's probably normally distributed. We will come back to the Shapiro test and actually turn it into an actual test and explain more. But for now, I can say that, yeah, this sample mean 4,000 does probably come from a normal distribution, all right? Yeah, okay, so that's all that I wanted to discuss with this lab. Once again, if you have any questions, make sure you ask during office hours or during the labs. And I'd like you to start using scripts rather than anything else. If you're feeling adventurous, you can look into the folder that I'm giving you over there, because besides the actual notes through a PDF, I'm giving you the R markdown version of it. So if you can utilize that to start writing things, I'd be very happy. But if you can, still try to use these scripts. Okay, that's all for this lab, and I will talk to you soon.